Welcome to Math 098, Chapter 2, Section 2, and we're just going to throw in some functions in here for you. And so there's basically three phrases that we have, but before we get to functions. But a relation is any set of ordered pairs. This is kind of a lame explanation. You might get a better explanation if you Google a relation. But a relation can be written as, any ordered pairs that you want. You can just make them up as you go, 0, 2, 1, 3. Maybe you repeat things like 1, 4, things like that. Or you could write a relation as an equation, such as y equals x plus 2. You can write it as a graph. So a relation can be just a set of ordered pairs. It could be an actual equation. It could be like a circle. Anyway, there's a lot of different ways of writing a relation. And the book, I think, says something about is anything that can be written as like you're mapping from one value to another, which is basically the same thing as an ordered pair. I'm not actually looking at the math, the textbook to get the definition. But you can see all of these have an ordered pair if I were to write them all out. So the domain, the really lame definition for the domain, is all of the x values. Now, if you look at a math book, they'd probably get a little bit more detailed with the domain as being x values that have a y attached to it. So as I'm looking at the domain of, let's say this one is 0 and 1, and there's no reason to repeat even though the 1's repeat there. On this one, you could say that x could be anything. So sometimes we say the domain is the set of real numbers. On this one, you could see that there's a smallest x value and there's a largest x value. So we might use interval notation to explain that one. And then same premise with the range are all the y values. So the y values on this one would be 2, 3, and 4. On this one, y could be anything. So the set of reals again. By the way, you're going to see me write it like this, a set of real numbers. You've seen that in Chapter 1. And then there's a smallest y value in this graph and a largest y value. So we might use interval notation on that one, depending on what's expected of you. So here's 4 graphs for you. I'm going to have to move this down so you can see it. And I'm going to ask you for the domain and range. And the easiest way to explain the domain is to go for the x values left to right. So you can see that there's a leftmost x value on this problem. 1, 2, 3, 4, 5, 6. I'm going to assume you practice interval notation with Algebra 2. And we use a bracket to say, oh, well, we want to include this x value all the way to -6. And as we move to the right, we're good until we get to this open circle at x equals -2, where the relation is not defined. So we're going to put a parenthesis here to say that x cannot equal -2. But then as we move to the right, this is called the union symbol. Let me write that down for you. It looks like a U without the little kickstand or whatever you want to call it. But in math we use this to say or. So all values bigger than -6, including -6, until we get to -2, or from -2. And as you look to the right, it's always defined to the right, so we can go to infinity. Sorry, I'm kind of on the graph now, but I didn't give myself much room. Now, as we look at the range in this problem, well, if domain we go left to right for the x values, it makes sense for the range to go from the bottom to the top. Well, if you look at the bottom of this graph, we're looking at that y value, which is a y value of -4. And think about it, do you want a parenthesis or a bracket? Well, it's a defined value, so we want a bracket. Now, as I go up, you have to go up on both sides. When's the next time that it's undefined? Well, you might stop right here and say, oh, it's undefined at 5, but is there a y value somewhere on here where it's defined? And that answer is yes. There's an infinite number of y's equal 5 right there. But I'm actually not even going to stop right there, because this arrowhead going up says that I could even get values larger than 5. So I can just go to infinity. I guess I should point out that anytime you write infinity, it's a parenthesis. And there's a reason for that. Something about being bounded or unbounded. You don't need to know that, but for sure we want to say infinity there. Okay, as we look at the next one, I'm going to try and squeeze it right here. So the first time that x is defined is at -6 again. All right, but this time I need a parenthesis because it's an open circle. It does not equal -6. Again, I'm going to assume you remember this from Algebra 2. Now, as I move to the right, there's an open circle right here at x equals -1. But is there a defined x equals -1? Yes, right here. So I don't have to say anything about -1 because there's a defined x value here. As we move to the right, it goes infinitely to the right. So now let's look at the range. All right, I'm going to try and squeeze it right here. Now from the bottom, some students get confused because they think it's just starting right here, but it's going infinitely down. So what we do is we say that we're starting at -infinity. As I mentioned before, anytime you have infinity, put a parenthesis. This negative is necessary because it's telling us the direction. It goes infinitely down, because remember, we go from the bottom to the top. And then the next time it stops, you might say at -1, but there's a defined value right there, so you don't need to worry about it. You might say it stops at 1, but it's immediately defined above 1. You might say it stops at 3, but we do have a y value, at -2, 3, y is defined. It doesn't actually stop until we get to 5, and because it's an open circle there, we're going to put a parenthesis, bottom to the top. I'm going to explain the next one just slightly different because I have a closed thing, closed graph, but I've actually seen teachers do this, and I think it helps some students, is they put a box around everything. So the whole graph needs a fit, and I would not do this if you have arrowheads. That's why I didn't do it on the first 2 problems. But this one is completely bounded between things. So what I'm getting at there is the domain goes from the leftmost x value, which this time it's -5. And it is defined, even though I colored over it, it is defined at -5, all the way until we get to 6. So by putting a box right there, it gives students a visual that we're going from the leftmost to the rightmost for domain. And for the range, we go from the bottommost, and again, it is defined at -3 to the topmost of +5. I don't know if that helps anybody, but that might actually help you understand this one as well. Doing a box. So the entire graph, the entire relation needs to fit inside of this graph. By the way, none of these problems are in the book, so you might need to print off these notes. -5 to 7, leftmost to rightmost, and the range is from the bottommost, -4, to the topmost, +4. Again, you probably don't want to do this box method when you have arrowheads on either side. All right. So what we have now is getting you to realize the benefits of function notation, because if like in years past, you probably looked at these problems and like your teacher said the f of x equals y and g of x equals y. Well, the problem is if you were to put both of those on the same graph, you would be confused which one is which. If you said y is a solid line and y is a dashed line, well, which one is which? Well, now by defining it with functions, f of x and g of x, now what you can do is you can look at this and clearly understand, I guess, what's happening. So I put this up here first because I believe the next couple slides will actually be looking at the same graph. But I wanted you to be convinced that function notation is necessary, which I know you have seen before. But before we do that, I just want to review mapping diagrams. So a mapping diagram usually gives you, different values for your domain. I think the numbers I used earlier were just 0 and 1. Maybe I'll give you one more. And then the range, maybe they give you, a couple different other numbers like, 5, 10, and 15. Well, the mapping diagram is just saying, oh, well, maybe we put arrows that say that the domain is your x value. It maps to a range of 5. Now, what makes this beneficial is maybe you have a problem like this, where instead of writing 1 twice, you can write 2 arrows, which is basically saying this. And then, this 2 could go, we could have ranges repeating as well. Now the issue is when we get to a function, so this would be the set of ordered pairs for this mapping diagram. Now you probably remember what makes something a function is the x values cannot repeat. So in my problem, let me just write it down. So in order to be a function, x values cannot repeat. So as I'm looking at this, 1 went to 10 and 15. In other words, my 1's repeated. Is this a function? This is not a function. So we wouldn't be able to use function notation on the example I just gave you here. All right, I think I have enough time to do one of these. So as you look at your x values in this problem, is this a function? Well, 3 and -3 are different numbers. 8 and 9, all of my x values are different values. So therefore, yes, this is a function. If you look at a graph, you can see that my -2's, my x values repeat. So this is not a function. You may have heard something called the vertical line test. We use vertical line tests when we're looking at a graph. And if I draw a vertical line test, if it crosses at more than one point, then it is not a function. And then here's another example. I think there's a few of these, which are just goofy problems. The input is people in a city. The correspondence is their birthday. Basically what it boils down to is can one person be repeated for their birthday? In other words, can somebody have more than one birthday? No. So is the people being repeated? The people are not being repeated, so this is a function. Yes, this is a function. Now if I switched it around, this would probably be not a function, because assuming there's more than 366 people in a city, then the birthdays could be repeated, and that by switching them, it would no longer be a function. This is probably a good place to stop the video and then record a second portion of this.